Hi, I'm Milind Singh, and this is the video presentation accompanying the final report titled NASA System Engineering Approaches, a system engineering case study of the Space Shuttle program, which was submitted to NYU Tandon School of Engineering for the course ECE GY 5213 Introduction to System Engineering. Let's begin by discussing what is system engineering and why it is important for the engineering process. System engineering is defined as the application of scientific methods to guide the conceptualization, prototyping, actualization, or to improve a structure, object, or system of objects, and to mitigate the problems that arise during the implementation of the project. While this is the book-bound definition of system engineering can be defined generally as the correlation and interaction of the various interfaces and participants during the development of a project. The function of system engineering is to provide engineers guidelines to base their systems upon. A big part of system engineering is modularity, giving the engineers freedom to design the components without needing to worry about compatibility with other modules. The modularity phase of system engineering states that design should be made such that a common interface can be found between subcomponents of different hierarchies and levels, so that compatibility is ensured between the different modules interacting from different various disciplines. Thus, the interfaces are specially designed such that modularity is the prime concern for the project. For example, the International Space Station used system engineering modularity principle. The design was chosen to be modular in the sense that there was supposed to be a base module which could which could be launched separately into space, and later on additional modules carrying additional functionality could be launched into space and added to the base module in space. There were a lot of international and local partners, and it was important to manage the interfaces properly. The National Aeronautics and Space Administration, commonly known as NASA, is an independent agency of the United States federal government responsible for the civilian space program as well as the aeronautics and aerospace research. NASA was established in 1958, succeeding the National Advisory Committee for Aeronautics, more commonly known as NACA. Since its establishment, most US space exploration efforts have been led by NASA, including the Apollo moon landing missions, the Skylab space station, and later the Space Shuttle project. NASA is supporting the International Space Station and is overseeing the development of the Orion multipurpose crew vehicle, the Space Launch System, and the commercial crew vehicles. The agency is also responsible for the Launch Services Program, which provides oversight of launch operations and countdown management for unmanned launches. NASA is involved in the development of space exploration, deep space research, communication and utility satellites, observing the observable universe, and the manned missions. NASA employs system engineering in their projects and designs. In fact, NASA has their own system engineering guidelines handbook define, defining the guidelines and protocols used by NASA in development of their missions. Let's look at a brief history of the NASA's manned missions. The X-15 rocket plane was the first ever to achieve spaceflight according to the International Aeronautics Board. Project Mercury and Project Gemini were test projects for NASA to check feasibility of space exploration and travel. The Apollo program is the first time humans were ever put in space. The famous Apollo 11 mission gave us the moon landing by Neil Armstrong and Buzz Aldrin. Later on, a space station program known as Skylab was developed, although it never completed in time and was later renamed to the Shuttle Mir program. The Shuttle Mir program was a joint collaborative between Roscosmos and NASA. This allowed them to service the International Space Station, which was earlier named to be Skylab, and then renamed to be the International Space Station after the involvement of 6 international partners. Later on, the Space Shuttle program gave NASA its own vehicles, its own fleet, to access the International Space Station and other missions. Later on, International Space Station saw its completion in 2010. There was also a Beyond Lower Earth Orbit program by NASA, which has not yet seen its inception and development. The report focuses on the system engineering principles employed during the development of the Space Shuttle program. So let's have a brief history of the Space Shuttle program. So the Space Shuttle program was initiated in 1972, the official name being the Space Transportation System. Its primary purpose was to be a partially reusable crewed flight lower Earth orbit spacecraft system, which could be used to transport satellites, crews, and International Space Station modules to the orbit. 5 space shuttles were constructed, and the fleet of space shuttle vehicles shared design properties physically. The major components being the orbiter vehicle, which would house the crew and the payload compartment, the 3 clustered Rocketdyne RS-25 main engines, a pair of recoverable solid rocket boosters, and an expendable external tank containing liquid nitrogen and liquid oxygen. In this section, we'll be discussing the concept development stage of the Space Shuttle program. In 1966, a joint study concluded by the Air Force and NASA concluded that there was a need for a new vehicle. This vehicle would be capable of space travel and will serve future space missions. The vehicle was needed to be reusable to be cost-effective method of space travel. It was decided that the most cost-effective method would be to have a partially reusable system, where either the system could be fully restored or partially restored after recovering after launch. In December of 1968, NASA appointed the Space Shuttle Task Group. The aim of this task group was to determine an optimal design for the reusable spacecraft. Study contracts were handed out to General Dynamics, Lockheed Martin, McDonnell Douglas, and North American Rockwell. The Space Shuttle Task Group later on determined that the shuttle would be required to support a space station, launch, service, and retrieve satellites, and support short-duration crewed missions. NASA announced a 4-phase approach for the space shuttle development. Phase A was to be a request for studies completed by competing aerospace companies. Phase B would be a competition between 2 contractors for a specific contract. Phase C would involve designing the details of the spacecraft components, and Phase D was the production of the spacecraft. Alongside listing the phases of development, the report also stated 3 classes for a future reusable shuttle. Class 1 was a reusable orbiter mounted on expendable boosters. Class 2 would use a multiple staging orbiter. Class 3 had both a reusable orbiter and reusable boosters. It was also determined that the space shuttle would have to have a payload bay of 15 by 60 foot, 100. The US Air Force and NASA came to an agreement where it was chosen that the Class 3 orbiter was the best choice for the nature of the program. The earlier straight-wing design was discarded because the space shuttle was required to carry heavier payloads than the design allowed. The straight-wing design was changed to a delta-wing design, which allowed for lower drag and landing as a glider. NASA and Air Force also determined that the payload capacity of the space shuttle would be around 65,000 pounds, and they need to have at least a 16 by 50 foot payload bay. NASA evaluated that the F1 and J2 engines from the earlier rockets that were in use were insufficient for the requirement. A contract was signed out to Rocketdyne to develop the more powerful RS-25 engine. 29 potential designs for the space shuttle were reviewed, and it was determined that a design with the orbiter having 2 side-mounted reusable boosters will be adopted. The design can be seen in the figure on the left side. The solid fuel boosters were chosen because of the lower cost and the ease of refurbishment after use. The orbiter contract was divided into the North American Rockwell solid rocket booster will be developed by the Morton Thiokol, and the external tank was developed by Martin Marietta. The design considerations taken into account during the concept validation stage allowed the Space Shuttle program to be a success. We will now see how the implementation of the Space Shuttle program worked. After the design requirements for the Space Shuttle program were determined, the design engineering phase began. The construction of the first Space Shuttle orbiter began in June 1974. The vehicle was named Orbital Vehicle 101 or OV-101. This vehicle was a test vehicle, and it did not include the shielding required for conditions in outer space. Rockwell oversaw the development of this test vehicle, which became to be known later as the Space Shuttle Enterprise. OV-101 gave engineers a chance to evaluate the feasibility of the design and the interfaces. The orbiter was also used for aerodynamic and mechanical testing. Rockwell was also contracted to construct the main propulsion test article 098. The equipment gave engineers the ability to test the Rocketdyne RS-25 engines without impacting the orbiter development. NASA decided to use ceramic tiles for thermal resistance of the orbiter. The decision was made in part because of the fact that tiles could be easily replaced and it would be a cost-effective method of reusing the space orbiter. Space Shuttle Columbia, or Orbital Vehicle 102, was delivered to Kennedy Space Center on March 1979. The new kind of shielding was completed 2 years after the first delivery, and the first flight of Columbia was on April 12, 1981. NASA commissioned OV-99, which was constructed by converting the STA-099 into an actual orbiter. This orbiter was to be named Challenger. Two more orbiters were later on added to the fleet, namely Discovery and Atlantis. The final addition to the Space Shuttle fleet was Endeavour, which was commissioned after the loss of Space Shuttle Challenger to an accident. On the right-hand side, you can see how the contracting of the various components and subsystems of the Space Shuttle vehicle was divided in the contractors. The Enterprise test shuttle was extensively tested for flight capabilities and landing patterns. The first test was a simple glide test, where the orbiter was carried to an altitude aboard a shuttle carrier aircraft and glided to a landing at the Edwards Airfield Base. The landing was completed successfully. The glider then underwent 4 additional flights before the next stage of testing. The next stage involved testing the stresses of an actual launch. The orbiter was then attached to the boosters and the external tank, and it underwent a shake test to determine whether the design would withstand launch conditions or not. The orbiter successfully completed this test too. Later on, the Enterprise was taken to a launch pad LC-39. It was attached to the external tank and boosters. The launch pad was verified for proper positioning of the spacecraft with the launch complex hardware. Enterprise was then retired to be used as a development vehicle for SLC-6 mission. On November 26, 1980, Columbia orbiter was mated with the external tank and the solid fuse boosters and was moved to Launch Center 39. The first Space Shuttle mission, STS-1, was the first crewed flight of the Space Shuttle Columbia. The shuttle was launched on April 12, 1981. The launch and return was successful. During this test, it was found out that several of the thermal protective tiles had fallen from the top of Columbia. Columbia re-entered and landed successfully on April 14, 1981. The tile shedding problem later proved fatal for the Columbia Space Shuttle, as we'll discuss later. NASA then conducted 3 additional tests after the Columbia launch. After STS-4 mission's success, the Space Shuttle was declared operational by NASA. The Space Shuttle program saw various obstacles during the development phase of the Space Shuttle program. The development of the RS-25 engines was delayed by 9 months, impacting the program schedule. The development was delayed because the engineers at Pratt and Whitney challenged the contract between NASA and Rocketdyne. During testing, it was found that the RS-25 engines displayed various issues with nozzle failures and faulty turbine design. The turbine wings would break off inside the engine, causing disaster for the engine. The prototypes were still given a go-ahead, and NASA ordered 9 RS-25 engines for the Space Shuttle fleet development. NASA faced a significant challenge in deciding the thermal protection of the orbiter. The earlier designs NASA used were ablative, meaning that they would perish upon re-entry into the atmosphere under the stresses of heat and temperature. They had to come up with a new material that could withstand the stress of re-entry and still be cost-effective to be used on a reusable orbiter. NASA chose to go with ceramic tiles, although ceramic tiles proved to be a controversial choice after the Space Shuttle Columbia accident. The impact of going with a different thermal protection system was that the shielding was incomplete at the delivery of Space Shuttle Columbia, and about 6,000 of the 35,000 tiles were missing. Apart from this, many of the tiles were damaged during the transit and had to be replaced. The logistical challenge arrived out of extrinsic factors and delayed the program by another 2 years. The shielding was observed to fall off the orbiters during various missions. This issue was well documented and known to the development team. This was not deemed mission critical, and the team was confident in the protection system. The Space Shuttle missions continued with the faulty design. The most significant challenges faced by the Space Shuttle programs were the accident that perished two of the fleet's orbiters, Challenger in 1986 and Columbia in 2003. Both failures were attributed to negligence and overconfidence in design, and a failure to follow protocols. NASA also ran into budget issues during the development of the program. Early during the development of the Space Shuttle, NASA had estimated that the program would cost 7.45 billion in development, non-recurring costs, and 9.3 million per flight. Earlier estimates for the cost to deliver payload to lower Earth orbit were as low as 118 per pound of payload, based on marginal or incremental launch costs, and assuming a 65,000 pound payload capacity and 50 launches per year. A more realistic projection of 12 flights per year for the 15-year service life combined with the initial development cost would have resulted in a total cost projection for the program of roughly $54 billion. The cost of the actual 30-year service life of the shuttle program through 2011, adjusted for inflation, was about $196 billion. The exact breakdown into non-recurring and recurring costs is not available, but according to NASA, the average cost to launch a space shuttle as of 2011 was about $450 million per mission. This was a significant deviation from the earlier estimates and caused various obstacles during the production of the space shuttles. The post-development stage of the space shuttle programs faced two significant challenges in the form of space shuttle accidents. In the course of the 135 missions flown by the space shuttle program, two orbiters were destroyed, with the loss of crew totaling 14 astronauts. The first incident was Space Shuttle Challenger, which was lost 73 seconds after its liftoff on the STS-51L mission on January 28, 1986. Later, the Space Shuttle Columbia was lost approximately 16 minutes before its expected landing on the mission STS-107 on February 1, 2003. Both these accidents shine a significant light on the ethical and protocol choices made by engineers during the development of the Space Shuttle accident. We will discuss the reason and cause of these accidents now. We will look at the disasters in chronological order. The Space Shuttle Challenger's disaster, which happened in 1986, happened as following. Challenger was the third shuttle in the fleet was the second to fly in space after Columbia. STS-51L was the final mission of the OV-099 vehicle. The mission carried a crew of 7 members and 2 satellites for NASA communications and observing the Halley Comet. On the day of flight, 28 January 1986, the orbiter exploded 73 seconds post-launch. The timeline of the accident corresponding to the time of max Q, which is also known as the maximum dynamic pressure, is as follows. Puffs of leaking O-ring within the first second of flight. During the 59th second, a visible flame from the O-ring was observed. At the 64th second, external fuel tank breached. On the 72nd second, the booster begins to rotate and fuel tank collapses due to the structural failures. On the 73rd second, the explosion and destruction of STS, traveling Mach 1.92 at 46,000 feet altitude at the time. The Range 50 officer activated the auto-destruct systems on both SRBs 110 seconds after launch. The delay was to ensure safety of the crew cabin. The incident was highly studied and controversial due to the fact that Thiokol engineers were aware of the O-ring malfunction and they tried to delay the launch one day before the actual launch. We will see how that timeline unfolds in the following slides. Rogers Commission. A presidential committee was ordered to investigate the cause of the Challenger disaster. This was done in light of the fact that Thiokol engineers were aware of the defect. The commission was led by Chairman William P. Rogers. The Rogers Commission, after his investigation and final reports, concluded the following. The faulty solid rocket motor joint and seal must be changed. This could be a new design eliminating the joint or a redesign of the current joint and seals. The administrator of NASA should request the National Research Council to form an independent solid rocket motor design oversight committee to implement the Commission's design recommendations and oversee the design effort. Thus, the faulty solid rocket motors were replaced with a newer design. The second recommendation was the shuttle program structure should be reviewed. NASA should encourage the transition of qualified astronauts into agency management positions. This recommendation was aimed at improving the management of the programs. Recommendation third stated that NASA and the primary shuttle contractors should review all criticality 1, 1R, 2, and 2R items and hazard analysis. Recommendation 4 stated that NASA should establish an Office of Safety, Reliability, and Quality Assurance to be headed by an associate administrator, reporting directly to the NASA administrator. The sixth recommendation was NASA must take actions to improve landing safety. The tire, brake, and nose wheel system must be improved. Thus, design changes were brought along to follow the recommendation. The last two recommendations were on behalf of crew safety and ethical following. NASA was to make all efforts to provide a crew escape system for use during controlled gliding flight. And the last recommendation stated that the nation's reliance on the shuttle as its principal space launch capability created a relentless pressure on NASA to increase the flight rate. NASA must establish a flight rate that is consistent with its resources. Rogers Commission's recommendations could be seen to reflect the event that took place the night before the Columbia Challenger launch. Thiokol engineers were aware of the O-ring deficiency and were aware that the O-rings would cause will cause leakage in the system if temperatures were significantly low. During the launch day on January 28, 1986, temperatures were below -1 degree Celsius, which was far from the safe 12 degrees Celsius designed for the O-rings. This deficiency was pointed out by theoretical engineers to NASA management, and management officials decided to not delay the launch any further and continue with the launch. This decision became controversial as it was deemed unethical and mismanagement of resources. NASA was advised to improve their safety protocols and to implement their system engineering principles more effectively. After the Space Shuttle Challenger incident, Space Shuttle flights were grounded for the next 2 years to implement the recommendations provided by Rogers Commission. Flights resumed after the recommendations were implemented and continued to go on for the next 16 years till the next incident, the Space Shuttle Columbia disaster. Space Shuttle Columbia started its final mission STS-107 on January 16, 2003. The mission was to carry the Space HAB Double Research Module, the Freestar experiment, and the extended duration orbiter Palais along a crew of 7 members to assist the mission. It was observed during the launch that a few pieces of the protective shielding of the orbiter had flown from the orbiter surface and struck the wing of the orbiter. The launch was successful and the mission was carried out successfully. During the mission progress, the damage on Space Shuttle Columbia were assessed. The documentation suggests that the damage on Space Shuttle Columbia was not significant and not critical enough to be a cause of concern for the crew. But later on, during the findings of Columbia Accident Investigation Board, it was discovered that the mission control knew that the damages were critical and the crew could not be returned to the Earth's surface safely. On February 1st, 2003, the the orbiter tried to re-enter Earth's atmosphere, but the left wing of the spacecraft detached, and the Space Shuttle Columbia disintegrated into pieces, immediately killing the crew and destroying the orbiter in an explosion. The timeline of the event with respect to Eastern Standard Time is 8:15 deorbit burn of 158 seconds duration to slow down the orbiter from 17,500 miles per hour at an altitude of 175 miles. 8:44 Earth's atmosphere entry interface leading edge temperature is 2500 degree Fahrenheit. 8:48 The first abnormal data reading in the left wing strain gauge. 8:49 was the speed is MA 24.5. Columbia rolls to the right as planned. 8:53 Columbia crossed California coast during peak heating period. 8:54 Signs of debris shed. Altitude of 2300,000 feet. First abnormal readings at mission control. 8:58 The thermal tiles were shed. 8:59 Last communication from orbiter. 9 The orbiter observed breaking up. This was the second time an incident would have occurred due to the negligence of NASA and overconfidence in the protection systems. This phenomena was this phenomena was coined as the deviation. The phenomena was coined as the normalization of deviance, which means that inconclusive testing results and deviations were allowed in the flights because there was confidence that the flight system would not break apart and the component would not cause any criticality issues. The normalization occurred due to successful launches and missions from faulty devices. The overlooking of this presumption costed the lives of 7 crew members on the Space Shuttle Columbia on February 1st, 2003. The Columbia Accident Investigation Board was given the charge of investigating the accident. The report provided by Columbia Accident Investigation Board states that a piece of insulation foam broke off the left bipod ramp of the external tank and collided with the left wing of the orbiter during launch. The piece of foam with a mass of approximately 1 kg breached the wing with a relative velocity of 500 km per hour and caused significant damage to the orbiter. The shuttle was past max heave and thus successfully sustained the damage without impacting the flight. The damage was well documented and observed by the mission control on Earth. Temperature variations in foam caused the vapor trapped between the foam to expand, providing enough force to loosen the foam pad and detach it from the orbiter. CAIB found that during the re-entry, the breach in the left lower wing allowed hot gases to enter and melt the aluminum truss structure of the wing. The deformed wing caused increased drag on one side of the orbiter, and the automated control systems tried to regain control of the orbiter. The wing broke off and the Space Shuttle broke apart under the high external aerodynamic forces, temperature, and pressure. The insulation shedding issue was, like the O-ring issue, well observed and documented before the accident. Although the design specification of the shuttle explicitly refrains from any shedding of any debris during launch, the foam shedding was dismissed as being trivial by NASA engineers, and this led to the accident of Space Shuttle Columbia. The CIB also concluded that the consideration and measures taken into account after the Challenger disaster was not followed, and another disaster stemming from the normalization of deviance effect had occurred. The findings of the Columbia Accident Investigation Board also concluded that the Space Shuttle program is not highly reliable. The Space Shuttle program was decided to be ended on in 2010, but was later extended 1 year and ended with the last flight STS-1. The mission was the 135th and the last Space Shuttle mission on board Atlantis. It was launched on July 8, 2011 and landed safely at the Kennedy Space Center on July 21, 2011, marking the end of the Space Shuttle era. After the Columbia accident, NASA tried to resolve this foam shedding issue and reported successfully solving the issue. But in findings by later independent agencies, it was found out that the foam shedding issue was still an issue on later flights after the Columbia accident. The Space Shuttle fleet still continued to serve after the Columbia and Challenger incidents, and retired after 30 years of service in 2011 after its 135th mission. The Space Shuttle program delivered 135 missions in total, with most of them being successful and essential in the development of the International Space Station. The turning points in the term of the Space Shuttle program were the two accidents, which saw a loss of 2 orbiters, 14 astronauts, and billions worth of investment. The Space Shuttle fleet was retired in 2011 after its 135th mission. The fleet has majorly been repurposed as a design inspiration for future manned endeavors. 3 remaining orbiters have been reused for development of other orbiters or have been given to educational and research organizations for display and study. The present locations of the orbiters as of 2019 are: Endeavour is a display at the California Science Center since 2012. Enterprise was on display at the Interpret Sea, Air and Space Museum in New York. Atlantis is part of the Space Shuttle exhibit at the Kennedy Space Center. Technological advancements in the modern era has always come with a price on the human resource. Historically, wars have given unprecedented growth to technologies. In the race of progressing ahead of the competition, ethical and protocol boundaries are often crossed, and design principles and requirements are often overlooked. System engineering principles try to mitigate such issues by deliberate redundancy of knowledge, simplistic division of labor, modular systems, and protocol for the development process, alongside a holistic view of the entire system. The Space Shuttle program was highly complex and intricate and involved a very large number of participants and interfaces. This led to a mismanagement of resources and time. The Space Shuttle vehicles were technological astonishments at the conception, but the disasters caused due to trivial reasons indicated a lack in proper management of the program. NASA and the collaborative efforts of similar organizations have rapidly developed technologies and applied them in their designs, but the cost of rapid development has been human life. At this outset, it is tough to justify the growth for the expense. System engineering principles are in place to guide future engineers to learn from past mistakes.